So this guy named Millikan is the guy who actually determined what the elementary charge of electron, or proton, of course, would be. So Thomson is the guy that discovered the electron, but Millikan is actually the guy who determined what its charge was, which is, I don't know if you probably agree with me, it's pretty important, okay? So how did he do it? He had this weird setup you see here, which let's take a closer look of what it actually looks like on the inside, which is right here. So what he did is he, through an atomizer, we kind of know it as one of those perfume bottle kind of things that you spritz out. What it does that it gives a charge to whatever's in here. So he put oil in here, and then he sprayed it out like that and created a bunch of oil droplets that had a charge because it would have ionized those oil droplets. And so then he had these oil droplets go through this small hole here. So obviously this is kind of cut in half so that the hole would go all the way around. All the other ones here would just fall in here because he just wanted to be able to analyze a little bit here. This is oil. And so just a few droplets would be able to go through because then he was able to figure out what's going on with them. Now, what's special about this chamber is this is parallel plates. These are charged. Okay, and we can have one that's charged positively, right? One positive plate and then one negative plate down here. And so depending on how this guy is charged, it will either accelerate downwards faster or even better, it will be attracted upwards, right? And these oil droplets typically had a negative charge. So we usually wanted the top plate to be positive because based on the charge of the top plate and the charge of this guy, we can get it to stay still. Why is that important? Well, the really important thing, if we have an oil droplet here that's staying still, we know that, and it has a, did I say a negative charge? I meant a positive charge. Oops. So if it's a positive charge, it definitely has, so if this thick guy has a negative charge, what's happening? Well, it's definitely being attracted upwards, right, by the electric force. But usually these oil droplets are still large enough that they have a gravitational force. So he was able to figure out how much positive charge to put on this to make these forces perfectly counteract each other. And once he does that, figures out and gets this to stay still, then we know, or some of the forces will equal to zero because it's not accelerating. And in that case, then we can look at the fact that the electric force is equal and opposite to the gravitational force. We can find the gravitational force on this oil droplet because we can actually find the mass of this oil droplet. And then from there, be able to figure out what the electric force was. And of course, the electric force has to do with the charge, and then use that to figure out the charge on this oil droplet. Okay, and so he was always able to find that the charge on the oil droplet was either 1.6 times 10 to the negative 19 or some multiple of that. Maybe it was 3.2 times 10 to the negative 19, right? So on and so forth. He was always able to find that it was a multiple of 1.6 times 10 to the negative 19 coulombs. And so that's how we figured out what the charge was, which was pretty cool. So he had this telescope here to really look in, and then he can figure out, because he has like switches here to be able to control the current going into these parallel plates. So he's able to turn it down a little bit or up in order to get a droplet to stay there. And he just did that a bunch of times and always found that it was about a multiple of 1.6 times 10 to the negative 19. So that was his process. This is just the notes of what I said. Let me make sure I didn't miss anything. Blue oil droplets between the horizontal parallel plates. If there's no charge on the plates, the droplets would just go, fall down because of gravitational force. And then if there's a charge, then some droplets would rise to the top, but some would definitely stay in the middle because some of it had Some of them had the electric force going upwards, gravitational force going downwards, and therefore there would be a counteracting of forces. Okay? And so that's the process. Oopsie. So if you want to write notes on that, obviously you can pause and write those notes down. I'm going to keep moving though. So again, he adjusted that voltage so that some oil drops were suspended in the middle, because then your electric force is equal to your gravitational force. Really, really important. And found that all those charges were either 1.6 times 10 to the negative 19 or multiples of that, right? 2 times that or 3 times that, because if an oil droplet had 3 excess electrons, well, then it would be 3 elementary charges, right? So he was able to conclude that the smallest he was always able to get was the 1.6 times 10 to the negative 19. So he concluded that that was the elementary charge, which is really just amazing if you think about that. So obviously we're not just going to learn about Millikan doing all these calculations. We're going to do the calculations. We're going to figure out how he calculated that, because we have that ability right now. So to do those calculations, what are we going to do? First, we're going to draw our free body diagram. I already kind of drew it earlier. So you're going to draw that same one where the electric force and gravitational force are counteracting each other, because that helps us figure out Newton's second law. And then we can determine the force equation. So obviously, we like it for when it doesn't accelerate, right? We want it either to be staying still or going down at a constant velocity. But if it is accelerating, always choose the positive direction to match the acceleration. Whichever way it's accelerating should be your positive direction. And then if it's not accelerating, it doesn't really matter which direction is your positive one. And then you calculate your unknown from there. Okay? Now, just a little note. Here's how he was able to determine the mass of the oil droplet, because you might be going, well, there was no scale in there. How do you determine a mass of an oil droplet? Well, you can determine mass using density. So density, oil has a specific density, right? And density is actually equal to mass divided by volume. So you're able to find the mass using the density of oil times volume, which if you're ever needing to do this, you will be given the density of oil. So density of the oil was measured. And then how do we find volume as well? Because you're probably thinking that's another thing, that we don't just have the oil drop. Well, the oil droplet is a sphere, and we know how to calculate the volume of a sphere. It's using this equation right here. Volume is equal to 4/3 pi r cubed. Okay? And so as long as you can get the diameter or the radius of the sphere, which is what he had his little telescope in there for, then he's able to calculate the mass. And there you go. So that is something you could be expected to be able to do. You will get these equations if you ever need to, okay? So how would we do these? We have a bunch of different scenarios, so we're going to go over all the different scenarios that we could have and how we could calculate charge using these scenarios. So let's assume that it's a positive charge and the oil droplet is remaining stationary. So if that's the case, which plate would have to be negative, which would have to be positive in order for this to be this kind of situation? Because we know it's stationary, we know therefore that the electric force and the gravitational force will be counteracting each other. Well, that means that if my electric force is upwards, this guy's got to be a negative plate and this guy's got to be the positive plate, right? And so again, as long as that voltage between the two plates is adjusted so that electric force is just as much as the gravitational force, there we go. It is staying still, okay? So again, how are we going to work out the equations for this? So this is scenario 1, so I'm going to put 1 over here. So we're going to look at Newton's second law, which is, of course, the fact that the sum of the forces... Oops, I was just about to put energy there. The sum of the forces equal to mass times acceleration. But it's stationary. It's not accelerating. So sum of the forces equals to mass times acceleration. That guy's 0. So the forces I had at work were the electric charge and the gravitational. I'm going to go ahead and make upwards positive. So I'm going to subtract that gravitational force. And that should equal to 0. Okay, so again, electric force here going upwards, gravitational force going downwards. And so you subtract those should equal to 0 because it's stationary, therefore there is no acceleration. So what do we find here? We found that our electric force is equal to our gravitational force. Okay, but we are still looking for the charge on something. So how do we calculate charge using electric force? There is an equation that says that the electric field is equal to force divided by charge. So I can rearrange that and get Q times the electric field is equal to force of gravity, which is of course mg. Okay, so got that. What if we don't have the electric field? How do we find the electric field between two parallel plates? Well, remember that the electric field between two parallel plates is its voltage divided by the distance between the plates. So I'm going to substitute that in for E there, and what do I get? I get Q times the voltage divided by the distance between the plates is equal to mass times gravitational acceleration, and that is how I find Q, the charge on the oil droplet. So it's M times G times the distance between the plates divided by the voltage between the plates. And of course, if you need to find mass, then you can use density times volume, and so on and so forth. So obviously that can be found out from there. So when it's stationary, really, really nice, right? If it's not stationary, we have a little bit more of a difficult scenario. So what do? Well, say we have a negative charge that's accelerating downwards, okay? Now you might right away think there's only one possible scenario that's happening here. And that is that it's accelerating downwards towards the positive plate. Because you're like, of course it's accelerating down to the positive plate. So the top one must be positive, and there you go. However, so that would be in the case where over here, this would be when, you know, gravitational forces downwards, electric forces downwards. So obviously this is accelerating downwards. Is that the only way it could accelerate downwards though? Is there no way that there could still be electric force upwards and it could still accelerate downwards? Absolutely there is. That would just be in the case where the gravitational force is much larger than the electric force. So really, there's actually a way that this could still happen even if this is the positive and this is the negative. So here we actually have two scenarios, okay? So in the first scenario, or the one on the left, we have acceleration that's smaller than 9.81. Acceleration on the left, we would have an acceleration greater, okay? So even though this is scenario 2, I'm going to call this A and this guy B, okay? Because we have two different scenarios here. And let's do our force equations for those two guys. So we have, for scenario 2, we have A, and that is when the electric force and gravitational force were still counteracting each other, but the electric force is still not large enough, so it's accelerating downwards. So if it's accelerating downwards, I need downwards to be positive. I know the sum of my forces is equal to mass times acceleration. In this case, that acceleration's got to stay there. So therefore, I know that my force of gravity minus my electric force is equal to mass times acceleration. And I'm going to keep that mass times acceleration in there. Now, I'm also going to account for the fact now, of course, we also know that gravitational force and electric force have their own equations. Okay, so I'm going to put those in. I'm also going to solve for electric force here. So we know electric force is equal to the gravitational force minus ma if we move that around. Electric force was Q times voltage divided by distance between the plates. Fg is, of course, mg. We want to subtract ma there. And then if I want to find Q from there, I multiply both sides by D and divide by V, the voltage. Okay, so what we end up getting is mg minus ma times the distance between the plates divided by the voltage. Okay, So there is one equation for Q, and that's, of course, if it's accelerating downwards, but accelerating at a rate that's less than 9.81 meters per second, because we know that that electric force is still slowing it down. It's just not slowing it down enough. Scenario B, however, was when it's accelerating faster than 9.81. So that means that we have gravitational force going downwards and electric force going downwards. So in part B, we still have downwards as positive, absolutely, and our sum of forces equal to mass times acceleration still. But here we add gravitational force and electric force because they're both headed downwards. And so here, if I want to find the charge, I'm going to solve for Fe. And that, in this case, would be mass times acceleration minus the gravitational force, okay? Which means Q times voltage divided by distance between plates is equal to MA minus MG. And, of course, I multiply both sides by displacement over voltage. And I get my charge here, okay? And that's how we solve for charge if it's accelerating downwards at a rate that's faster than 9.81, meaning the electric force and gravitational force must be going downwards. Okay, so they do look very similar, the two, except for in the first one, we subtract mass times the acceleration from the mass times the gravitational acceleration. And in the second one, it's the other way around because, of course, we know its actual acceleration is greater than gravitational acceleration. So there we go. There's scenario 2. Let's go to scenario 3. And that's where we have a positive charge. Okay. And it's accelerating upwards. Okay. Well, there's no way to not have gravity going downwards. So gravity's still going downwards. So what can we then probably say about the electric force? The electric force is still upwards, but since it's accelerating upwards, it's just accelerating upwards at a larger rate, right? So it's going to be larger. Whoops, I'm supposed to say Fe. Okay, so that's what we can really say here. So we know that the electric force is larger. So this is definitely got to be the negative plate on top, positive plate at the bottom, and that just means that this negative plate is providing a bigger force than the gravitational force could. I'm going to redraw this just to make it a little bit more obvious that the electric force is greater than the gravitational force because it wasn't super obvious in the other one. And so that's a situation in which it would accelerate upwards, okay? So let's look at what the equations look like in that scenario. Scenario 3, accelerating upwards. So upwards must be positive. Sum of our forces equal to mass times acceleration, which it is accelerating, so we can't cancel that out. Okay, in this case, upwards force is electric force, so Fe, and then I subtract Fg because, of course, that's downwards, and that should equal to mass times acceleration. Okay, solve for Fe, and that's Ma plus Mg. Or Fg, or whatever you want to say. We know electric force is Q times the voltage divided by the distance between plates. And so if I want Q, of course, I multiply both sides by d over v. Okay? And so that's a case in which you would add the acceleration and the gravitational acceleration. And there we go. That's how we find that scenario. So that's when it's accelerating upwards. Okay, what other possible scenario could we have? We have it when it's at rest, when it's accelerating upwards, and when it's accelerating downwards. So what other situation could we possibly have? Okay, so we have in our fourth scenario a negative charge that's accelerating downwards at a constant velocity. Constant velocity. What does a constant velocity mean? So it's still moving downwards, but it's just moving downwards at a constant velocity. So here's the question. Is it accelerating? No. When things move at a constant velocity, they're not accelerating. So should we treat this any different than scenario 1? No, absolutely not. Except for in scenario 1, we did have the positive charge. So here we still know electric force upwards, gravitational force downwards. They are equal and opposite. So this is where Millikan really had to figure out, okay, if something's stuck in the middle and it's not moving, obviously no acceleration. But he was also able to easily look at situations where it was moving down at a constant velocity, because that's still the same scenario where there's no acceleration. So since we still need an electric force going upwards, we definitely need this to be a positive plate and this guy to be a negative, so we have electric force going upwards. They're still equal and opposite, but it's just moving down a constant velocity because there's still no acceleration. And so when we set up our Newton's second law here, we're like, okay, well, neither one is positive, neither way is positive or has to be positive because acceleration, because that's still zero. So when we know that we're taking electric force and subtracting gravitational force equaling mass times acceleration, we know that's still zero. And therefore, this is going to look exactly the same as scenario 1. So mathematically, exactly the same thing happening. It's still a slightly different scenario, right? Where now we have a negative charge. And so, of course, we have to look at our plates being different than scenario 1. But mathematically, scenario 1 and scenario 4 are exactly the same. So anytime you see that constant velocity, that constant speed there, don't let it fool you, because that's what it's there for. It's trying to fool you. It's trying to make a fool of you. So just don't let it. And that is how Millikan figured out what the elementary charge is.